Welcome to the session of strength of material. Here today we will discuss about stress and strain tensor. So basically in this course or in this lecture our objective is confined to find how the internal forces are basically quantified in a body and how the strains are generated at different points in a body. Okay. So first of all, what we're gonna analyze is the stress tensor. Okay. So suppose we are considering this is a body which is subjected to various forces like this. Now, if you segregate a small part of it, you're segregating it, okay, and you have to define a coordinate system, that is y, x and z. Okay, as you're segregating this small part from this system, what we can consider, if you consider this segregated part is a block like this, and we are considering only the basic forces which are acting at the surface, that are the normal forces. Okay, that means if you consider this as a block having 6 faces, so basically the 6 internal force that are acting on every surfaces, that are the 6 internal forces are acting at 6 surfaces. Okay, so basically this is an elemental cube which is basically segregated from the system, and the system as it is in equilibrium, this small elemental part is also in equilibrium. Okay. Next, what we're gonna discuss is about the stress and the traction vector. So basically this is a body which is under equilibrium, and if you cut a oblique cutting by which you splitted this body into 2 parts, that is the first part and the second part, and you considered a point, and at that point basically some force is acting, a general type of force which is acting in any particular direction, and the area around this point you are considering it as delta A. Okay, so now what we have is basically the force del F, that is in particular direction. Okay, and this will have some particular direction of force in x direction, some direction of force in y direction, some direction of force in z direction. If you define this is the coordinate system, and this is basically the y direction, x direction, and this is the z direction. Okay, so this force which you considered a generalized force, so if you resolve it in x direction, y direction and z direction, you will get the desired force. Okay, and what you want to define now is basically the intensity of force, that is the intensity of force. What is intensity of force? This intensity of force is basically defined by the quantity del F by del A, limit del A tends to 0. Okay, so basically this intensity of force is defined by the quantity is del F by del A when limit del A tends to 0. That means you're considering a point on this equilibrium, on this system which is in equilibrium, and on this point some force is acting, and the area around this point you considered as the delta A, and the intensity of force is basically del F by del A, where limit this del A tends to 0. That means this point is, the area around the point is almost considered or constricted to a point. Okay. Now, what we consider, this quantity we define as traction or stress vector is del F by del A, is defined as traction or stress vector. Okay. And this stress basically acting is a generalized formula of traction or stress vector. If you consider this stress in the x direction, suppose if you denote it by Sx, okay, and that will be what? Limit delta A tends to 0, and the force which is acting in x direction by delta A. Why delta A, not delta x? Because you are considering this area to be very small, which is basically constricted or converges to a point. So basically a point does not have any sort of orientation. So it is, we are least bothered about the orientation. Only we are considering the stress in the x direction as del Fx, that is the force in the x direction by delta A, where limit delta A tends to 0. And this is the stress component in x direction. Same thing for Sy, if we consider, that will be limit delta A tends to 0 del Fy by delta A. Same thing for Sz, that is limit delta A tends to 0 limit Fz by delta A. Okay. So what we are getting, these three are the traction vectors. Okay. So these traction vectors, basically the traction components. Okay, this Sx, Sy and Hz are what? Are the traction component. Okay. Now what we gonna discuss is, based on this idea, we gonna define stresses at a point. Now what we gonna discuss is basically the stresses at a point. Okay. So this is the axis system what we defined: x direction, y direction and z direction. This is the body which is in equilibrium under the application of this loading. And if we cut a plane which is perpendicular to x-axis, then it will look like this, and that is basically the part 1. This is the part 1, this is the part 2, and we are cutting a plane which is perpendicular to x-axis. Okay, and this is basically, if you consider, this is the positive direction, positive x direction. Okay, and this is the point which is under investigation. Okay, and around this point is that area. Okay, and that area, if you consider, is basically delta A x. That is the area which cuts the x plane. Okay, so now what we gonna consider, that on this plane, the small elemental area, if you consider, on this elemental area, if the point P is situated, which is under investigation, one force which is acting perpendicular to this area, that is del F xx. If you denote it by a subscript xx, that is the force which is acting in the positive x direction. One force which is basically acting in the y direction, that is del F xy. Okay, and another force which is basically acting in z direction, that is del F xz. Okay, so basically what we are getting is, basically, as this body is under or subjected to different types of loading, So it is very obvious that every element on this body will be subjected to the forces in different directions, and that forces can be dissolved into three basic directions, that is in the x direction, that is in the y direction, and that is in the z direction. Okay, and if you consider this is the part 1, and the first subscript what we have x, it is denoted the plane at which we are cutting, so basically it is an x plane. Okay, and the second subscript denotes the direction at which this force is acting. Okay, so same thing if you draw it for part 2. For part 2, the forces which you consider for part 1, all the forces will be in opposite direction. This force will act in opposite direction, that is del Fxx. As this force in the z direction was in this direction, it will be in opposite direction, that is del Fxz, and the corresponding this will be in the downward direction, that is del Fxy. Why it is in the opposite direction? Because this is the internal force. To maintain this body in equilibrium, if you join this one, the net force within the body will be 0. So to cancel the net effect, so the internal forces are in opposite direction of it. Okay, so basically what we can consider is that the forces in part 1 is the mirror reflection of part 2. Okay, so basically when you cut the plane in x direction perpendicular to the x-axis, you are getting three components of forces, and the corresponding stresses, if you say sigma xx, if you denote it, that is the stress vector or traction vector, that is what, del Fxx by del Ax limit delta A tends to 0. This is the first component of stress what you are getting. Another component what you can consider is basically the sigma x y, that is limit delta A tends to 0 delta Fxy by delta x. Another component what you can consider is basically the sigma xz, that is limit delta A tends to 0 delta Fxz by delta x. So basically when you are cutting the plane perpendicular to the x-axis, so you are getting the three components of stress. Okay, three component of stress vector what you are getting. Okay, so another thing, this stress is basically depending on two attributes. One is the direction of the force, another is the orientation of the area. Okay, so basically this is the force which is normal to that plane, so this is basically known as normal stress, and this the force which is acting parallel to that element, so basically this is the shear force. Okay, it is denoted by tau xy, and this is tau xz, but in generalized form you can also write it in tau xy form also, but it is generally denoted by tau xy, that denotes the shear force, that is the stress which acts parallel to the surface, and this acts, normal stress basically acts normal to the surface. Okay, so this is the condition what we get, the number of components we get is 3 when we cut the plane perpendicular to the x-axis. Initially we cut the plane perpendicular to the x-axis. Now if you want to cut the plane perpendicular to the y-axis, then this shape will identically look like this. Okay, and this is the axis system. So the three basic force in three basic directions will be, one in the y direction, same thing, delta Fyy, because this y is the plane which is cutting, and the direction of force is denoted by the second subscript. Okay. Same thing for a shear force that will act in the x direction, that is a positive x direction, that is delta y x. Okay. Another thing, another direction what we will get is in the z direction. Okay. And if you draw the identical part, if this is part 1, another is part 2, and that will be exactly mirror image of this part 1. So all the forces will be in opposite direction because these are the internal forces. Okay, clear? Same thing which can be we can denote the intensity of force. Intensity of force, that is basically tau yx, that is limit delta y tends to 0 del yx by delta in y. Okay, so this is the intensity of force or the stress vector. Okay, and this is basically shear in nature which acts parallel to the element. Okay, another thing, tau y z, that is limit delta ay tends to 0 delta yz by delta ay. Okay, another is basically the normal stress, that is sigma yy limit delta y tends to 0 delta yy by delta ay. So when we cut basically the plane perpendicular to the y-axis, we get here also the 3 component of stress vector. Okay, another plane that is remaining, that if we cut the plane perpendicular to the z-axis, we also get the 3 components like sigma z, that is tau zx and tau zy. Okay, the 3 components when we cut the plane perpendicular to z-axis. This is the component that we get when we cut the plane perpendicular to the y-axis. So in total we are getting 9 component of stress vector. So basically at a point if we define a stress vector, it has 9 components and it is denoted by a stress tensor, a 3D stress tensor, and that will be denoted or indicated by a matrice, and that will be denoted like this: sigma x, tau xy, tau xz, tau yx, sigma y, tau yz, tau x zx, tau zy, and tau z. So in this matrix what we are having, the 9 component of stress, and this is basically known as 3D stress tensor. Okay, this is basically known as 3D stress tensor. Okay, and this can be written also in some generalized form, in the form of, so the generalized form is basically sigma 1, sigma 11, sigma 12, and sigma 13. Initially it was sigma x, sigma tau xy. So this can be written like this. So here the direction is 1, 2, and 3 instead of x. Okay, this generalized stress tensor can be written as sigma ij, where I is basically varying from 1 to 3 and j varying from 1 to 3. Okay, so this is basically a generalized 3D stress tensor. Okay.